So good afternoon, everyone. I'm Norman Wildberger, and we're here at the University of New South Wales. In this little chapter on the history of mathematics, we're going to look at a very contentious period that had a lot of innovative ideas that were, let's say, rather controversial. So we're going to talk about sets, logic, and computability. And the time that we're talking about is the latter half of the 19th century into the earlier part of the 20th century. And some of the key figures that we're going to be talking about are Georg Cantor, who was the introducer of set theory, who lived from 1845 to 1918. Richard Dedekind, who was responsible for one of the prime theories of real numbers from 1831 to 1916. Kurt Gödel, brilliant Austrian logician, lived from 1906 to 1978. And Alan Turing, 1912 to 1954, was one of the sort of pioneers of computability and the role of the modern computer. Okay, so these issues are closely connected with some of the fundamental problems in analysis, going back to the 17th and 18th and 19th century questions. And I guess one of the driving questions, sort of lurking behind the scenes, was the question, what is a function? Of course, we all have an intuitive idea what that means, but the role of that word has shifted historically quite a lot from Newton's time to Euler's time to the modern 19th and 20th century definitions. So one of the interesting aspects is that this function really expanded quite a lot. To Euler, a function was something like a polynomial, or maybe a power series. Or maybe a rational function. But later on, people were looking at more general things, and one of the motivations for this was the development in analysis due to Fourier, who introduced something called Fourier series. So if we have a function from, say, the interval -1 to 1 to r, then Fourier introduced this idea that you could represent it in the fashion 1/2 some a0 plus some sum from n equals 1 to infinity of an cosine n pi x plus bn sine n pi x. Okay, so this is valid for x in -1, 1. This is called a Fourier series, and it expresses an arbitrary function, let's say even a function with some differential problems. Maybe it has some non-differentiability points, or maybe it's even not continuous. Something like that. The function could be like this. And Fourier somehow said, well, we can still think about this as being sort of a sum of very nice functions. These cosines and sines, after all, are just very nice oscillatory functions with perhaps variable periods. Okay. And moreover, he showed how to find these coefficients, these so-called Fourier coefficients, by integration. So an was the integral from -1 to 1 of f of x cosine n pi x dx, and bn was the integral from -1 to 1 of f of x against sine n pi x dx. Okay, so Fourier's theory was very controversial at the time, and in fact, even though it ended up being a very, very important development for applications, it was actually rejected when it was first appearing, because people didn't really know what this equal sign meant. It wasn't entirely clear what nature of equality was being supposed here, and it was also not entirely clear, how it could be that an arbitrary function, whatever that means, could be expressed as a sum of such nice functions, albeit an infinite sum. So there were a lot of problems that, developments that stemmed from Fourier's theory, and in fact Cantor's work was very much motivated by problems coming up from this kind of analysis. So Cantor was interested in analysis, and he was interested in these kinds of questions. In particular, he was interested in the kinds of discontinuities that functions could have. And he was interested, therefore, in studying sets of points in the interval -1 to 1 with an idea of classifying the kinds of possible problems that functions could have, let's say. So it was motivated by this that he introduced what's now called set theory. And these days, this is a very accepted form of mathematics, but in Cantor's day, it was highly controversial. And many prominent mathematicians opposed Cantor very vigorously, so much so that Cantor ended up perhaps feeling a lot of mental stress because of the opposition that was directed towards him. And set theory, as we'll see, had some theoretical problems too. There were some paradoxes that were discovered, which we'll talk about. And then mathematicians tried to resolve those paradoxes, and one way they did it was to try to sort of introduce logic or a systematic framework for logic into mathematics, and that created a whole new development, which then eventually also connected rather closely with notions of computability. Okay, so this is the rough story that we want to talk about in today's lecture, some of the people who figured and some of the ingredients here. So there's a very big topic, and I'm only going to be able to give you a sort of a rough overview of what's going on, and really there's a lot more to say. So if you do want to have some more information about this, I suppose that I could refer you to my MathFoundations series, YouTube series, where I eventually propose to talk about all these kinds of issues at some considerable length. Okay. Today we're just going to give an overview. But I do want to be honest with you and let you know that my point of view is quite different from the majority of mathematicians' points of view. Okay? I have a rather heretical position with respect to these subjects. So in my view, all of these subjects are really subjects that perhaps should have quotes around them. Okay? In other words, it's hard to actually pin down what these things actually precisely are once we look carefully at them. And a picture that you might have in mind to understand that, this is very diagrammatic. Okay? Suppose that's mathematics, and maybe over here we have philosophy, and maybe over here we have computer science, very roughly. Right. Then set theory, as far as I see it, sort of fits something like this. It sort of straddles mathematics and philosophy, and so does logic too, actually. And computability sort of straddles mathematics and computer science. And it becomes rather problematic to define clearly what parts of these subjects belong to mathematics and what parts of the subjects belong to philosophy or to computer science. And one of the key problems is that it's hard to pin down the meanings of the key words precisely. So the key problem in all of these subjects, I feel, is that it's difficult to pinning down precisely the meanings of the words involved. The meanings of the words or the terminology that we're using. And that goes right back actually to the original question of what is a function. It's not so easy to say precisely what a function is. Similarly, it's not so easy to define exactly what a sequence is or what a real number is or what a set is or what a theory is, what a statement is, and even what a computer is. So a lot of the terms that we end up using in this discussion are perhaps best thought of as having quotes around them. And really that's a core reason why there's some ambiguity involved. But nevertheless, let me give you something of the standard story with respect to these topics. Okay, so the story really begins in the 1870s, where Cantor made the following definition. Okay, a definition. So he said that a set is a collection of distinct or well-defined objects. It's a collection of distinct or well-defined objects. And probably Cantor himself realized that there were some kind of problems with this. So an initial kind of problem is, what kind of objects are we allowing? Well, we'd like to sort of restrict ourselves to mathematical objects rather than psychological or fictional objects. But nevertheless, saying what that is exactly is problematic. But more than that, there was also self-referential kinds of questions. For example, what about, let's say, U, which is the set of all sets S? Now that we've defined sets, we have this idea of what a set is, so why can't we take the collection of all sets and call that U? Well, that's a very strange set because, first of all, it has a lot of things in it. But in particular, since U itself is a set, it's inside here. So this set U is, amongst other things, it has many things in it, lots of sets. But amongst them is the set U itself. So we have a set which contains itself as an element. How can that be? So the mind boggles a little bit. So Cantor realized that there was something a little bit delicate about this situation. And in fact, later on, this kind of thing led to serious problems, but not initially. Initially, it was quite a useful thing because it allowed Richard Dedekind to frame an answer to a problem that had been bothering mathematicians for a long time. And that was, he answered the question of what precisely is a real number. And this was also around the same time, in the 1870s. And of course, people had been working with real numbers in some sense. People had been working with Stevin's idea, going back to the 17th century, that a real number was something like 47.1350012, and then some decimal expansion. But when you try to develop a theory of arithmetic with such infinite decimals, there are quickly some problems that come up. And mathematicians realized that infinite decimals was not perhaps the best way of thinking analytically about what's going on here. So Dedekind proposed a different idea, and Dedekind's idea became known as the theory of Dedekind cuts. Okay, so let's say we have our number line, and here is pi, okay, which is 3.1415, etc. So what Dedekind said is, all right, imagine just rational numbers for a second. So imagine this is the rational number line, just consisting of ordinary rational numbers. Then pi is not a rational number, so it doesn't, strictly speaking, belong to the number line. It's like a gap in the number line. So Dedekind said, all right, well, let's use the fact that it's a gap. There may be a hole right there where we think pi is, but that hole separates the rational numbers into set A on one side, and let's say the set B on the other side. Okay? So something like pi sort of gives us a splitting or partition of the rational numbers into two disjoint subsets, A and B, which have the property that every element in A is less than every element in B. So A is less than B for all A in A and B in B. And so Dedekind said, okay, what we can do is we can think about what the number pi is by saying, not just a correspondence, why don't we just define pi to be this splitting? This splitting now called a Dedekind cut. Okay, actually the example that Dedekind used was not pi, because trying to imagine this splitting for pi is actually a little bit problematic, or at least challenging. What he actually used was the example of square root of 2. And for square root of 2, things are much simpler. For square root of 2, you can define these sets. For example, you could define B to be the set of numbers A which are bigger than 0, such that A squared is bigger than 2. A in the rationals, of course. And A is just the complement. A is B, a complement. So for this irrational square root of 2, this subdivision was relatively easy to get hold of algebraically, but for other ones it's more problematic. The advantage that Dedekind realized is that if you view things this way, then the arithmetic of real numbers could be established relatively painlessly. So you could establish the arithmetic at least theoretically. So this allowed a theoretical derivation of arithmetic with real numbers. Even though in practice, in fact, it was completely impossible. Basically, if you wanted to do arithmetic practically, you really had to go back to the infinite decimals of Stebbin.
Sorry, I got lost in all the Dedekind stuff. I'm sure to understand it.
Okay, so Dedekind's idea was that if we want to define what a real number is, what we can do is we can think about it as being a subdivision of the rational numbers into two disjoint subsets. That is what a real number is, according to Dedekind. It's not an infinitesimal, it's not a Cauchy sequence or equivalence class, it's just a splitting of the rationals into two pieces, like you get that with a knife, you chop the rationals into two pieces. So in order for this to work, of course, you can see that you have to use infinite sets. And so Cantor's theory was important here for infinite sets because they were a basic ingredient. Okay, another important use of Cantor's theory was in deciding what a function was. So suppose you have a function f from the real numbers to the real numbers. So now we could think about such a function as being essentially an infinite table. Here's x, and here's f of x. So here we're going to list all the real numbers, say 4.01356, blah, 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 and f of x happens to be 17.894, whatever it is, blah, blah, blah. So you go through all the real numbers, and you figure out what the corresponding f of x is, and you write it down. And you imagine this whole table. Okay, it's a huge thing. It's sort of an infinite set. You can think about it as ordered pairs if you like. And in fact, it turns out that even listing them is problematic. But in any case, with the language of set theory, you are allowed to say that this is what the function is. The function is an infinite table like that. In contrast with that definition, there's another definition which is quite different, which ended up playing an important role. So there's another way of thinking about what a function is, that it's basically a rule given by an algorithm. Well, an algorithm, or maybe a formula, or program. But the essential aspect is that it must be finite, finitely specifiable. So for example, e to the x, one way of writing that is summation n equals 0 to infinity of x to the n over n factorial. There's a finite formula that defines a function quite a different way than this one. So this way of thinking about what a function is a very finite one. That's, of course, more in the spirit of modern computer science. While this one here is more open-ended, requires an infinite amount of memory space, and it's rather theoretical. It's hard to give an example this way. So this is an important dichotomy that occurred in the field. There's sort of some tension between these two points of view to what things are. We might call this the choice point of view, and this sort of the algorithm point of view. Although it wasn't entirely clear to the earlier practitioners that there was this separation, somebody who really pointed this out very clearly was the famous 20th century philosopher Wittgenstein. So Wittgenstein really pointed out that mathematicians are really playing this kind of game a little bit where they have two quite different ways of thinking about something like a function. And sometimes it's convenient to think about it this way, and other times it's convenient to think about it this way. And there are challenges with both ways. Okay, another interesting development that occurred here is that because Cantor was able to now think about sets as being rather arbitrary, including infinite sets, he ended up realizing that there was some kind of hierarchy, or there were hierarchies of infinities. And let me iterate again that I don't believe any of this. Okay, so this is the standard dogma. For me, all of this should be in quotes. I don't buy any of it, but okay, I'm telling you the standard story. Okay. So according to Cantor, there wasn't just one infinity, there was a whole hierarchy of infinities that went on up and up and up and up. Okay? And one way of sort of describing this is through something called ordinal numbers. Ordinal numbers, and another way is through something called cardinal numbers. Okay, this is a distinction that doesn't really play a crucial role for finite numbers, but ordinal numbers are sort of like counting, where you're saying first, second, third, fourth, roughly. So ordinal is like first, second, and so on, while cardinal numbers are like 1, 2, and 3, the actual sizes of things. So Cantor and then other mathematicians realized that you could sort of arrange a hierarchy of ordinal numbers. So here's the ordinals, hierarchy of ordinals, just the very beginnings of it. So first of all, we're going to start with 0, the 0th one. And that is going to be the simplest set of all, the empty set, the set with nothing in it, which we can think of as having a pair of braces, or we can think of it sometimes just represented by this symbol too. Those are two different symbols for the empty set. Okay, now if we're going to just build things up just using set theory, then we can take sets of sets. So the number 1 could be defined to be the set consisting of 0. We've just defined 0, so we take the set consisting of 0, and that's the number 1. And then the number 2 is defined to be the set 0, 1. The 3 is the set 0, 1, 2, and so on. And usually that's as far as we go. We say and so on. But Cantor realized that that's just the beginning. We could transform that and so on into a new ordinal. We could create a new ordinal W by taking the sets that we've already constructed and forming a big set out of all of them. So we create W by taking the set consisting of all the sets that we've produced up to that point and taking the union of all of them. So the union of 0, 1, 2, 3, all the way up to n, and keeping on going. This is a new infinite ordinal. It's like the first infinity. Okay, so for me this is problematic in that there are these 3 dots around. These 3 dots here between 3 and n I'm kind of willing to buy, because that just represents some finite segment that we're too lazy to write down. This 3 dots here is much more problematic to me. All these other numbers that go beyond n to out to infinity, and we're collecting them all in some big bracket, and we're claiming that now we've got some object, and we're going to carry this object around now with us. I agree with the ancient Greeks that such things are not allowed. In fact, a lot of mathematicians prior to Cantor's time did not believe that it should be allowed. In fact, a lot of Cantor's contemporaries believed that it was not allowed. But Cantor insisted, and there was an interesting theory. He said, well, we can go further. Why don't we take the next one? How do we take the next one? How did we go from 1 to 2? Well, we just added 1 to the previous one. So what we're going to do is we're going to take the numbers 0, 1, 2, and so on, just as before. But now we're going to throw in W as well, or omega. And then we can do W plus 2, and then eventually we can get to 2W. 2W is like 0, 1, all the way up to W, and then W plus 1, and then W plus 2, and all the way there. And then we can eventually go to W squared, and then W cubed, and then W to the W, and then we can go W to the W to the W, and then we can go W to the W to the W many, many times, and it gets bigger and bigger and bigger. And this is just the beginning. Okay, so modern set theorists, this is just baby stuff, and the ordinals are some massive, hard to comprehend thing that goes on beyond. Okay, there were also cardinals. Cardinals were something different. Cardinals were ways of measuring sizes. Those are ordinals. There are also cardinals. Okay, so cardinals represent the size of sets, the size of a set. Okay, and well, we have finite sets. The finite set sizes are just the ordinary numbers. The first infinite set is n0, which is the size of the set 0, 1, 2, and so on. So we declare that that set has size Aleph naught. So this is called Aleph naught. In fact, the sizes of W plus 1, the sizes of these things are all Aleph naught. Adding 1 to this one doesn't change its size in any real way. So these are all, these infinite sets, the ordinals that I've defined here, are all Aleph 0 size. But Cantor, in a admittedly brilliant piece of work, realized that there was a bigger size. Okay? So we come to Cantor's diagonal argument, where he shows that there are bigger infinities around than just Aleph 0. All right, so this is a very famous argument that Cantor had, which turns out to run through this entire subject. So it comes up many, many times in many different forms and ends up playing an important role in the computing side of things that Turing and Post and others developed later as well. So Cantor's argument was the following. He said that basically he showed that there is no list. There is no list of real numbers. No infinite list. In the sense that if somebody has a list, say the first one is, say, 0.3451200, and there's your first real number. And then here's the second real number, 4.5, well, let's just make them all between 0 and 1 to make things simpler. So here's a second real number, and then here's a third real number. So for simplicity, let me just restrict to real numbers 0, 1. So suppose that we had a list of all the real numbers between 0 and 1. Suppose somebody had such a list. Then Cantor said, no, that is not a complete list, because I can come up with a real number that's not on your list. And he did that just by reading down the diagonal here. So he looked down the diagonal, ignore everything else, and then over here, he would write down here is a number which is not on your list. He would change the first one. That's a 3, so I'm going to, instead of writing a 3, I'll write a 4. The next one's a 1. Instead of writing a 1, I'm going to write a 2. Instead of the 4, I'm going to write a 5. If the next one happens to be 0, instead of 0, I'll write a 1. So I'm writing a new infinite decimal, which has the property that it differs from each of these existing ones on the kth diagonal. This cannot be on the list, because it's certainly not the third one on the list, because the third one here differs from the third one here, so it can't be the third one on the list. Similarly, it can't be the 3,000th one on the list, and it can't be anywhere on the list at all. That was a very ingenious and lovely argument, but that shows that the size of the real numbers is bigger than the size of the natural numbers, strictly bigger. And so it deserves a new name called LF1. That's the definition of LF1. It's the size of the real numbers. And we've shown, this argument shows that this really is a strict inequality, that if you believe all of this, that the size of the real numbers is strictly bigger than the size of the natural numbers, because you can't list them. Okay, so at this point, things were going really reasonably smoothly, I suppose, despite all the controversy that was developed. But it didn't last for too long. Okay, so the whole theory came crashing down. So around 1900, set theory collapsed, which is a rather remarkable development, because mathematical theories don't usually collapse. Right? Mathematics is supposed to be sure and confident and correct. But what happened is that people discovered paradoxes. Okay, and actually some of them were sort of minor paradoxes that just were sort of on the fringes, but then there was one paradox that was clearly unavoidable. No one could get around it, and that really collapsed the whole thing. So what are the kinds of paradoxes that were involved? Well, one of them was called the Burali-Forte paradox, which goes back to the Ordinals. Okay. So if you look at the Ordinals, and you take the union of all the Ordinals, That's how we always create. There's essentially two ways of creating new ordinals. One is by adding the last one that you had onto the set of the previous ones. And the other way is to take the union of everything up to a certain point. So Burali and Forte said, well, why don't we just take the union of all ordinals? That should be another ordinal. Okay, but which one is it? Because we've taken the union, this should be bigger than all of the other ones. But if itself is an ordinal, how does that work? There was another paradox discovered by, I think, Richard's paradox. Which goes back to Cantor's diagonal argument. And Richard said, okay, well, what happens if we try to name these real numbers? So imagine naming real numbers. Okay, so like maybe give all possible names. So pi is, the length of the units, length of a circle. Okay, and square root of 2 is the length of a diagonal. Okay, so we have a list of names, of descriptions of real numbers. Well, there's only a countable number of possible texts that you can write down in English. Because only countable. Countable means the same size as, i.e., same size as the natural numbers. The reason is because there's only a finite number of texts of a given size. We're talking about texts with 30 elements, then there's a certain finite number of such things. And number with 31 elements, another finite number. And so you can list all those possibilities with some sort of imaginary, some big dictionary that just keeps on going. But the point is you can list them 1, 2, 3, 4. Okay, so the real numbers that can be named are countable, but we've just supposedly established that there are uncountable real numbers. So that must mean that there must be real numbers out there that are not nameable. In fact, most of the real numbers are not nameable, in the sense that there's no way of describing them at all. Even if you have some huge hard drive and you go on for years making some description, you just cannot describe these numbers. So most real numbers are unnameable. Okay, but that wasn't the worst paradox. The worst paradox was discovered by Bertrand Russell. Who was a prominent mathematician, English philosopher. And his paradox was, okay, we talked about that set U before. So U was the set of all sets. And this set contains itself. That's a rather remarkable property of a set, that it actually contains itself as an element. So Russell said, okay, how about this set? I'm going to define a new set. Let's define the set of all sets that don't contain themselves. Like most sets that we know, they don't contain themselves. So let's look at the set of all sets that don't contain themselves. And then Russell asked, does X contain itself? And the answer is yes and no. Okay, I'll leave it to you as a fun little exercise to see why the answer is both yes and no. And that's not a good situation in mathematics where the answer of a question is both yes and no. And so this was a major consternation. People said, uh-oh, we've been too grandiose in our tackling of infinities with all these sets and so on. Something is wrong. We have to backpedal. We have to fix things. So people looked around for ways of fixing things. Okay, and for many decades there was then this enormous discussion about how to fix set theory, because people wanted set theory to be fixed because set theory was the underpinning of analysis. The analysis of the time really required things like integrals, Fourier series, infinite sets were being used in analysis, so the analysts wanted a justification for what they were doing. In fact, even the real numbers require an infinite set theory in order to create them. So if set theory collapsed, then a lot of other subjects were also starting to look very wobbly. In particular, analysis was starting to look very wobbly. Okay, so people scurried around, and there was a lot of activity, and it would be quite remarkable for somebody in that time to come to our time now and to come into a classroom and go, well, what do you guys think? You know, how is it resolved? How did you fix the problems? And you go, what problems? Most undergraduates are blissfully unaware that there were these incredibly deep foundational problems in mathematics that really divided the subject. These days, okay, it's all largely invisible. It's really quite interesting turnaround of things. In fact, nowadays, set theory is established as the standard thing. Everybody uses infinite sets all the time. We're always saying, consider this infinite set, and consider this infinite set, and consider this function from this infinite set to that infinite set. So how did that happen? Well, that's an interesting story that takes us to the next developments having to do with logic and sort of harnessing logic to try to build up a proper theory of set theory and to cover the gaps. All right, so logic. So classical logic goes back to Aristotle. It has its roots in philosophy. It's really historically a subject of philosophy. It goes back to Aristotle, who laid out various laws of logic. For example, Aristotle is a man. All men are mortal. Therefore, Aristotle is mortal. That's the kind of logic, elementary example of the kind of logic that Aristotle enunciated, dealing with propositions, usually involving concepts from everyday life. People started trying to algebraicize, algebraization, let's say, of logic started to happen due to a fellow called De Morgan, who you'll know from De Morgan's laws, and George Boole. So they kind of developed an algebra of logic and propositions. And then this was developed into, taken and extended into a certain school of thought, the logistic school. This was then one of several schools of thought that developed as a way of trying to lay foundations to move forward on the problems of fixing set theory. Okay. So the logistic school was the outgrowth of mathematician Frege, and also Russell, who we talked about, and his friend Whitehead. And they wrote some huge treatise where they laid out the foundations here. And basically their idea roughly was that mathematics rests on logic. So there's this logical system where you start with logic and then you build up mathematics from the logic. Okay, the logic of propositions along the lines of Aristotle, but more algebraic. In principle, it sounds okay, but it turned out to be very unwieldy, and most mathematicians could hardly read this huge book that Russell and Whitehead wrote. It's a very big, hard to read thing. So I guess it wasn't universally accepted. There was another school of thought that emerged called Intuitionism. School of Intuitionism, whose prominent leaders were, first of all, Kronecker, and then Brel and Lebesgue were involved. Poincaré was sympathetic to this. Brouwer was, I think, probably the main figure. Weil, also an important figure. So Intuitionism kind of rejects this logistic framework. So here there was, maybe I should say, so there was an important aspect of axiomatics. So built into this logic were certain axiomatic rules that we just had to accept and definitions that we just had to accept, including sort of building in of the natural numbers. So roughly speaking, Intuitionism wants to preserve the natural numbers as a God-given thing of our intuition. Okay? So for them, the natural numbers, namely the 1, 2, 3, and so on, these were the fundamental objects of mathematics, according to Kronecker. Kronecker had a famous statement where he said that God created the natural numbers, and everything else is the work of man. So to Kronecker, the numbers 1, 2, 3 were sort of God-given, and that was a thing that we can just intuit using our mathematical intuition, and we can't really sort of say more precisely what the natural numbers are. They're just there. But once we accept the natural numbers, then we can build pretty well everything else from the natural numbers. Okay, there were other aspects of it. So there was some debate about something called the law of excluded middle, which was a logical point. But basically, they had Brouwer especially had a more intuitionistic, almost maybe somewhat mystical view of what was going on. But that was not the only school, not the only two schools. There was also a third school, which is the School of Formalism. And its main proponent was Hilbert, who was another one of the very prominent mathematicians around the turn of the century. And Hilbert's idea was that, well, mathematics consists of theories, and each theory is built up or starts with axioms and symbols and rules of inference. And then developing the mathematics was basically a formulaic kind of thing that you just did using the axioms and the various rules. So it was like a mechanical game almost. It became rather mechanical. He wanted to mechanize things to guarantee solidity. He wanted it to be like something where there was no possible interpretations or vagueness. Hilbert was not interested in interpretations. He was just saying, let's just stick with the symbols and forget about what the symbols mean.
Sorry, so these are actual math schools, not schools of thought.
These are schools of thought. These are schools of thought, yes. That they weren't physical schools. They were sort of disciplines or schools of thought that were would have adherents in various places. Okay, but one of the problems with Hilbert's scheme, although it's a rather attractive kind of idea, and in fact, actually, in some sense, perhaps the ideas go back to Leibniz in some form, who also looked for sort of mechanical ways of trying to create mathematics. But the problem here is that of consistency. How do we know if we set up some arbitrary system that's sort of unconnected from the real world? How do we know that it's actually consistent? How can we guarantee it? And he had this program that he hoped that somebody would come along and prove that these systems were consistent. Well, that turned out to be dashed by the work of Gödel, so that's what we're going to talk about next week. We'll talk about how Gödel established some results that basically sank Hilbert's dream of creating a standalone formalist system for mathematics, and how then that was sort of taken in different directions by the growing interest in computers and computational issues by Turing and Post and Church and so on. So there's then links to this side of logic and the new development of computability. We'll talk about that next time.